Hello, hello. Shall we start? Okay. Yes, thank you. So hello everyone. We are Héctor and Roger. We are research engineers at CISC, which is I will say a kind of newly released zkVM, basically a zero-knowledge virtual machine. And today we are here because we would like to try to explain a little bit how we did proof recursion in the context of a zkVM. Okay, in the context of zkVM, proof recursion and aggregation are, I will say, quite distinct from a standard context. So the main idea of this presentation is not only to introduce the concept, basically the from zero part of the title, but we would like to emphasize the main differences or the main ideas that we have been cooking in the proof aggregation in our zkVM. Okay, so let's start very quickly from the basics. What is a zkVM? A zkVM, I'd like to define it as I will say a virtual machine or a piece of software that allows you to prove that some program has been computed, given an input to a program properly. Okay, basically, let's imagine that you have a program written in a high-level language like in Rust. Okay, and then with a zkVM, you can generate a proof that for a given input, for a given instance of the problem, let's say the output of this program is correct. Okay, and then this proof, well, in fact, you can build a lot of applications on top of this proof. One deal application is that you can send it to a mobile phone and you can try and you can verify this proof very quickly. Okay, so that the mobile phone doesn't have to re-execute the computation from the beginning to the end. The mobile phone only has to verify such proof. Okay. Okay. In order to do that, I'd like to describe it in a very high level detail, like in a three-step process. Okay. The first one is the one that I like to call the compilation step, in which basically you have to translate the program description in the high-level language to a description that the machine that you are working on understands. Okay, so this is the traditional compilation that they have in programming languages. So for example, you have a Rust program, the traditional way of expressing or doing this transpilation is by compile it down to RISC-V opcodes. Okay, so basically you translate the program to RISC-V. The second stage is what we call the arithmetization, in which once you have a program that the machine understands, you have to again translate it to something that the proving system understands, because the main objective is to generate a proof. Okay, so basically arithmetization, you translate it to something that is amenable for a proving system. And finally, we have the proving stage, in which the idea is that you are trying to find a satisfying witness or a satisfying execution that basically passes all the arithmetization of your particular problem. Okay, so there are problems like the previous one, which are very easy to understand, are very easy to arithmetize. But then, in order to build a zkVM, you have to arithmetize, let's say, a full, complete language. Okay, so in the case of zkVMs, the most traditional example is RISC-V. Okay, as you can see in this diagram, RISC-V is composed of many components. It has a lot of instructions, it has memory, it has registers, it has an assembly, and so on. Okay, and the main idea, so that you can build a zkVM, is that you have to be able to arithmetize all these components. Okay, there are many ways of doing that, and there have been many attempts during the past in order to do that as quick and as easy as possible. One idea will be, okay, let's try to arithmetize all this problem all together. Okay, so you have to come up with a set of constraints that basically do all the things, but this is very complicated. And a second idea, which is, I will say that an awesome idea, is to do it in a piecewise manner. Okay, in the sense that you divide very naturally the arithmetization in all the components as you will do in the RISC-V problem. Okay, so for example, you have your processor, you have your memory, you have the program, you have one component dealing with arithmetic operations, what is known as the ELU, and so on. Okay, and then through something that we used to call the bus, okay, which basically is a channel of communications between all the components, like in a regular CPU, you prove that, for example, if you're in the processor and you want to perform a computation that you don't know how to arithmeticize, you basically assume this computation in the processor, and then in the specialized component that knows how to perform or knows how to prove this operation, will prove that operation. Okay, so from one side, we assume that operations are correct, and from the other side, we prove that operations are being done correctly. Okay, this is from the arithmetization perspective. From the proving perspective, you have yet another problem. Okay, the traditional way of doing that is by computing a monolithic proof, or what is known as a monolithic proof, which basically is, okay, we have all this arithmetization, we have the boost, we have all the components, let's basically compute a full proof of all at once. Okay, well, there are many issues regarding this approach. One is this, the proving time is, I would say, quite huge if the program that you are trying to arithmeticize is very large. Okay. Another problem is that because you are going for a monolithic approach, a lot of these components are underused. Okay, it's because not all the programs use the same components in the same frequency. Okay, so this is an example of a typical program that is using, let's say, in an irregular manner all the components, and at the end, the main issue is that you will end up proving, or you will end up using computation for some components that in fact are not being used during the proofs, but you still have to pay for it. A second better approach, that is the approach that we are using in the VM, is what we call a VATCO, variable degree composite proof, in which instead of trying to generate a full proof of all the things all at once, you generate a proof for all the components individually. Okay, so you have a proof of the correctness for your main processor, you have a proof of the correctness for your binary, and so on and so forth for the rest of components. Okay, so at the end, what you end up with is, let's say, with a cluster of a group of proofs altogether that are proving that all the components are doing the things correctly. Okay, the problem with that is that you will need, if you don't do something else, you will end up needing as much verifiers as the number of components that you have. Okay, so here the missing piece is that we are using proof aggregation or proof recursion in order to reduce the problem of having, let's say, multiple proofs to a single proof. Okay, so that the verifier basically verifies the single proof in order to be sure that all the rest of the proofs are correct. Okay, so what is proof aggregation? Basically, the main idea is that you have your, let's say, your instance of problem one, or you have your one of the components in the top, you have another component in the bottom, you generate a proof of all these two components, and then you arithmeticize not the problem itself, but the verifier of the proving system that you choose. You send the two proofs to this, let's say, to this verifier prover, and then you generate a single proof attesting that the previous two proofs are valid proofs. Okay, you can do this with two proofs or multiple proofs. But there is still one issue that we need to tackle, and is the dependency between all the components. Because remember that all these components are communicating through the bus, and so we have to ensure that the assumptions and the proof parts of this bus are being done correctly. Okay, so one of the ideas, or the way that we do that, is by computing what we call an auxiliary trace, okay, in which, in some sense, we commit to the parts of the trace that are performing a particular operation. Okay, so let's say that the main processor is assuming some arithmetic operations in some part of the traces, and then the arithmetic is proving such operations. What we do basically is computing, let's say, a single representative, okay, what we call the accumulated value of of these assumptions from one side and of the, let's say, the proof parts on the other side. And finally, what we do in a future step is ensuring that the two accumulated values in two sides are precisely the same, okay? Ensuring that the assumptions in one part and the proofs in another part have been the same, okay? And you are not trying to lie, you are not trying to introduce newly operations and so on. Okay, this can be repeated for all the components, right? Because, for example, the main compressor communicates through the bus through many other components, okay? So at the end, you have the accumulated value of the main processor, you have the accumulated value for all the components, and you prove that all the sums are equal to the main sum. Okay, and finally, one single example that I'd like to highlight, or one way that we do that, is via the grand sum argument, okay? In which we use basically, let's say that we use a verifier challenge, a verifier message, in order to ensure that the accumulation of all these values have been done correctly.
So now that we have introduced the problem, I will explain how we can properly aggregate all those proofs so we can just get a single one. So the first thing that we need to understand is that how we can reduce those proofs into one. So what we can do is we can write the verifier as an arithmetic circuit, which then will allow to generate a new set of constraints. So now you can generate a new proof of the existing one. This will allow us to create circuits that are verifying more than one proof. So then we will end up getting a single one. If we were on a monolithic approach, this would be very straightforward because you have one proof and it's an independent one. So the verifier using Fiat-Shamir interactive protocol can generate all the randomness that the prover needs. So it can automatically verify that proof. However, we are as Héctor explained, we are in a bad cop approach. And in this approach, all these proofs are connected with the global constraints. And in order to ensure its correctness, there's a global challenge that's a randomness that all the different proofs need to share in order to verify the correctness of the global constraint. Therefore, this randomness that I will explain later on how we can calculate it, it cannot be obtained just for a single proof, but you need information from all the different ones. And then in order to verify a bad cop proof in this first stage, the first thing that you need to do is you need to provide to the verifier this extra information, this global challenge, so that they can verify this initial proof. And then later on, we will verify that this global challenge that was a free input and that it was not verified initially, it actually is correct and matches the global contribution. So additionally, in this first stage, which we call the normalization stage, we do three things. We verify the proof, and then we prepare for each instance the contribution to this randomness. And also, as Héctor explained, each instance will either assume or prove some part of the global constraint, so we will prepare those inputs so that later on we can aggregate it together. Then we reach the aggregation part, which is where the fun begins. Basically, here there's an example of a recursion of 2 to 1, but you could do a recursion n to 1 if you want. Basically, what's happening here? You have two different proofs that has been normalized and prepared, and now you want to aggregate together. So you create a new circuit, which is called the aggregator circuit, which instead of verifying a single proof, it verifies two proofs together, or more if you want. Also, this aggregator circuit does two very important things. The first one is it starts recalculating the randomness, the global randomness. So you have two instances and you get those partial contributions to the randomness and you aggregate it together. I will explain in the next slide how there's two different ways of doing that. And also it also accumulates the partial contributions to the global constraint. So at the end we can verify that it matches. And so this process is done recursively until you get one single proof. So there's one important thing to notice here. Here you have like two normalized circuits that are processed by an aggregator circuit. But if you think about it, on the second iteration, you will need to aggregate two aggregator circuits into a new one. So it's very important that the normalized circuit and the aggregator circuit generate the same type of proof, so you can blend them together and you can aggregate them indistinctively. So now there's a very important question. Okay, you have like n proofs and you want to merge, you want to reduce it, but which, or do you is there any specific order that you need to follow? This basically depends on how you define the global challenge, which is the randomness that all the instances share, and there's two different approaches you can take. The first one, and probably the more naive one, is hash-based. So basically you could define a tree so in which all the leaves are the contributions to the randomness of each instance, and then the prover and verifier agrees on the order of that tree, and when the verifier performs the aggregation, then it needs to follow that order that was previously accorded with the prover, because otherwise, if you change two leaves of the tree, the global root the root will be different, and then and the things will not match. This is an issue because you are forced to follow that order, and additionally, if you want to go to a very performant approach, it has the issue that it requires log-n steps, because you will need to compute the lower level of the tree, then the next one, and this way up until top. This means that even though you have like thousands of machines, if you have like, for example, 64 instances, you will need to do 6 steps. There's no way you can speed this process up. And that's a limitation, for example, for zkVMs, that right now we're trying to go proving Ethereum in real time. There's, however, another approach that we can take, and it's based on elliptic curves. And it's basically we can take advantage of the very fun, amazing property that elliptic curves provide, that addition is commutative, which means that basically you have all the initial contributions, and if you're able to map these contributions to a point of the curve, you can add those points, and then you can get a resulting point, and you can map it back to your field or your field extension, so that then the verifier will be able to aggregate in any order and still reach the same result. This has the downside, if you want to say, that you need to find a specific curve which for your setting, but it's much more powerful because you break the dependency of the ordering, so you can aggregate in any order. You can also, it's way easier to distribute the computation because you can just, you have different servers that aggregate independently their proofs, first come, first serve, or the way they want. And at the end, they will always reach the same final randomness because addition is commutative. So now we have reduced all the, we have aggregated all the proofs together, and we have one, we need to generate one final proof. Why? Because first we need to check that the global challenge that was originally provided as a free input, it's actually correct. So basically, while you were doing the aggregation, you were checking that you were reconstructing this challenge. So now you check that it matched the one that was initially provided. And the second thing is you need to verify those global constraints, because you had like partial, you had partial parts of that constraint, and now you need to verify that when you added everything together, the result was 0. So everything that was assumed was proved. So basically, this is like an overview of what I was explaining. We have here like several instances. We go through the normalization stage, which we generate a first proof that verifies this initial one and prepares the inputs for aggregation. Then we have an aggregation stage, which, for example, in this case, you can see a 3-to-1 aggregation. And then finally, we generate this final proof that verifies the global constraints and the global challenge. Here, there's one thing that you can have, like maybe the first proof is too big, so you may need a compressor stage in which you reduce the first proof by generating a proof of the first one. That's just for compressing, but usually this will not be the case. And well, everything so far that we've explained was mostly from an abstract point of view. We've been applying this in ZISC, which is a zkVM that we've been developing for the last year, at the beginning in Polygon, and now as an independent project. And then Jordi we'll explain in a couple hours in the retro stage. But here you can see some properties. And here's some numbers. For example, for us, at Zisk, we're using Starks and Fry. And here you can see that for some numbers about a single recursion step, how long it takes, or how much memory does it use, or the proof size. And that's all. Here you can see our repository, as we are fully open source. And if you have any questions, feel free to ask.